space Habraham in it. And we are, I don't know if YouTube got the intro, but yeah, you know how it is. So we gotta learn organic chemistry. It's a really interesting, and don't mind this, it's just my next biking videos. Could you tell me? Well, the keyboard's off. How? Well, it's 11%. It's so weird. How did the keyboard just lose all the battery? Turn it off to charge. Can I use it while charging? Now let's use the laptop keyboard. Let it just charge. You know what? We gotta start using this guy. Let me see how it is. Tough. Free. No. Nope. Okay, maybe perplexity you can take rest. Now give Oh, you don't need a CS3, right? Okay, so that's correct. SN1. Let's watch E1 E2 reaction. Where's this guy?
Build an app with your name on. However, if the substrate, in this video, we're going to go over SN1, SN2, E1, and E2 reactions. So the first thing you need to know is if you have a methyl substrate, for example, like methyl bromide, the reaction will proceed using an SN2 mechanism. It really doesn't matter what type of solvent we're using or if we're using a base, it's going to be an SN2 reaction. Now, if we have, let's say, a primary substrate, like ethyl bromide, in this case, it's going to be an SN2 reaction unless you decide to use a bulky base, in which case it's going to be an E2 reaction. Now, let's say if you use a strong, unhindered base like hydroxide. It's a strong base, but it's not bulky. The predominant mechanism will be SN2. However, if the substrate is sterically hindered, then you could get the E2 reaction. SN2 reactions work with substrates that are not sterically hindered. But if it is, then the E2 can win in competition against the SN2 reaction. So if you have a sterically hindered base and a primary substrate, it's going to favor the E2 reaction. But if the substrate is not hindered, sterically hindered, then it's going to be SN2. Let's say if you use a strong base like hydroxide or even methoxide.
Wait.
Now,
To check out SN1, SN2 first.
In this video, we're going to focus on nucleophilic substitution reactions. There's two common types that you need to know, the SN1 reaction and the SN2 reaction. But let's begin our discussion with the SN2 reaction. This is a second-order nucleophilic substitution reaction. The rate of the reaction depends on the concentration of the substrate, and it depends on the concentration of the nucleophile. It's first order with respect to the substrate, and first order with respect to the nucleophile, but it's second order overall. That's why it's an SN2 reaction. 1 plus 1 is 2. If you double the concentration of the substrate, the rate will double. If you double the concentration of the nucleophile, the rate will double. If you triple the concentration of the substrate, the rate is going to triple. If you quadruple the rate of the nucleophile, the rate will quadruple. What's going to happen if you double the concentration of the substrate and triple the concentration of the nucleophile? In that case, the rate is going to increase by a factor of 6. If you triple the concentration of the substrate, quadruple the rate of the nucleophile, the rate will increase by a factor of 3 times 4, which is 12. So what exactly is the substrate? Well, the substrate is basically an alkyl halide. So here we have 2-bromobutane. We're going to add a nucleophile. Let's use iodide. Iodide is a good nucleophile. And in this reaction, iodide will attack the carbon from the back, expelling the bromide leaving group. The SN1 reaction occurs in a single step. It's a concerted reaction mechanism. All bond-breaking processes and bond-forming processes occur at the same time. Now, this reaction occurs with inversion of stereochemistry. The bromine was in the front, but now the iodide is in the back, since it attacked the carbon from the back. So let's find out what the configuration was before. If Br is in the front, H is in the back. So let's assign Br a value of 1, the ethyl group 2, methyl 3, H is 4. So if we count from 1, 2 to 3, we can see that we have, this is going clockwise, so we have the R isomer. Therefore, the product is the S isomer. The hydrogen is now in the front, and if you count it, it's 1, 2, 3. It appears to be R, but because hydrogen is in the front, you have to reverse it, so it's S. So the configuration of the Claus center, it reverses in the SN2 reaction. As you can see, no carbocations were formed, and therefore the SN2 reaction is not subjected to carbocation rearrangements. Wherever the leaving group was located, the nucleophile is going to be on that same carbon. Now, why is it called a nucleophilic substitution reaction? As you can see, the leaving group was replaced or substituted with a nucleophile, and so it's called the nucleophilic substitution reaction. Now, SN2 reactions, do they prefer primary substrates or tertiary substrates? It turns out that an SN2 reaction works best with a methyl substrate. It's most reactive with these. And then it works well for primary substrates as well, but for methyl substrates it's better. And it doesn't work very well for tertiary substrate. Now let's compare a methyl substrate with a tertiary substrate. Let's see why. So here we have methyl bromide. And we're going to draw also tert-butyl bromide. Let's use hydroxide as a nucleophile. Now, if you react hydroxide with methyl bromide, it's going to be an SN2 reaction, and it works pretty well. But if you try to react hydroxide with tert-butyl bromide, it doesn't work well. Why do you think that's the case? Why does the first reaction work very well, but the second one does not work very well for an SN2 reaction?
There's no carbon.
In order for the hydroxide to react with the carbon atom or with the methyl bromide, it has to attack the carbon so it can expel the bromine atom. In order for it to do that, the carbon has to be accessible. Hydroxide has a difficult time getting to this carbon because of these bulky methyl groups. The methyl groups they basically protect this carbon atom from the hydroxide group. And so because of steric factors, it's very difficult for hydroxide to access the carbon. And that's why tertiary substrates don't work very well. The carbon atom that has the leaving group is virtually inaccessible. It's very difficult to get to. So the SN2 reaction for a tertiary substrate is very, 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 very slow. So basically, it's almost non-existent. So SN2 reactions work well whenever you have an unhindered substrate or an accessible carbon atom to attack. Now let's talk about the mechanism of a SN1 reaction. So let's say we have tert-butyl bromide, and we're going to react it with a negatively charged nucleophile. Let's use iodide again. So the first thing that happens is the leaving group leaves. You have the formation of a carbocation. Now at this point, carbocation rearrangements can occur. But there's not going to be any rearrangements in this particular structure because the plus charge is on a tertiary carbon. Tertiary carbocations are more stable than secondary and primary ones. So after the carbocation is formed, the nucleophile attacks it. And so in this case, we get tert-butyl iodide. So if you have a negatively charged nucleophile, the SN1 reaction occurs in 2 steps. The rate of an SN1 reaction is equal to the concentration of the substrate times K. It doesn't depend on the concentration of the nucleophile, because the first step is rate limited. The slow step is the formation of the carbocation. It takes a long time to produce this carbocation. The second step, the combination of these 2 ions, is pretty fast. So that's why SN1 reactions are known as first-order nucleophilic substitution reactions. Overall, it's first order. Now, what if we have an SN1 reaction where the nucleophile is not negatively charged? It's neutral. In this case, the nucleophile is also the solvent. Whenever the nucleophile is the solvent, you have a solvolysis reaction. So in the first step, the leaving group's going to leave. And so we're going to get a secondary carbocation, which will not rearrange.
Just a minute. Gotta get my water.
And water, the nucleophile, can attack it from the back, or it can attack it from the front. So because it can approach the carbocation from both sides, we're going to get a racemic mixture. If it attacks it from the back, like the SN2 reaction, this is going to produce the inverted product. We'll talk about the final product, which is an OH, but I'll show you how to get the
configuration.
So the inverted product will look like this. If it attacks, let's say, from the front, then we're going to get the retention product. Now keep in mind, this is not an equal racemic mixture. We don't get 50% R, 50% S. Rather, it's more like 60-40 / 70-30. We get more of the inverted product than the retention product. And the reason why that's the case is because there's a bromide ion that, even though it's disassociated from the carbocation, it's not always very far from it. So the oxygen of water has a partial negative charge. Bromide has a negative charge. So if water attacks from the front, as you can see, it's going to be repelled by the bromide ion. And so it's less likely to attack from the front. But if it comes from the back, there's no such repulsion. In fact, it's attracted to the carbon in the back because the carbon has a partial positive charge. In fact, well, it has more than a partial positive charge. Once the bromide leaves, it has a positive charge. So it's definitely want to attack it from the back. We don't have the influence of this bromide ion repelling the water molecule. So that's why the inverted product is still slightly more than the retention product. Bromide doesn't block access from the back, it blocks it from the front. But now let's finish the mechanism. So let's say water attacks it from the back. Initially, we're going to get a product that looks like this. Whenever oxygen has 3 bonds, it has a plus charge. And then we need to use another water molecule to get rid of this hydrogen, giving us the alcohol. So whenever you use a neutral nucleophile, the SN1 reaction will occur in 3 steps. If you use a negatively charged nucleophile, it will happen in 2 steps. The third step involves the removal of this hydrogen. Now, what about the substrate? We said that for an SN2 reaction, it works better if you have a methyl or primary substrate because the carbon atom is more accessible. What about for an SN1 reaction? What's the case here? For an SN1 reaction, tertiary alkyl halides or tertiary substrates work better than secondary ones. Methyl substrates don't work very well. Now, why is that the case? Now, if you recall, the rate-limiting step, the slow step, is the formation of the carbocation intermediate. To increase the rate of that first step, you need a more stable carbocation. It's very difficult to form an unstable carbocation, but it's easier to form a stable carbocation. And because tertiary carbocations are more stable than secondary carbocations due to hyperconjugation and the inductive effect, tertiary substrates work better for an SN1 reaction than secondary substrates. So methyl substrates are the least stable because the methyl carbocations are, let me take that back. Methyl substrates do not work well for an SN1 reactions because the methyl substrates are the least stable. So that's what I wanted to say. And so that's it. That's why tertiary alkyl halides work better for an SN1 reaction, is because the tertiary carbocation is fairly stable compared to the other carbocations. Now let's work on some more SN1 reactions. And let's focus on rearrangements. Let's not worry about the stereochemistry of the reaction. So let's say if we have 2-bromo, 3-methyl-butane, and we're going to react it with methanol. If we use water, water is going to produce an alcohol. If you react an alkyl halide with an alcohol, for the SN1 product, you'll get an ether. But let's propose a mechanism for this process. So the first step in an SN1 reaction is the formation of the carbocation intermediate. So the leaving group have to leave, and we're going to get a secondary carbocation. The reason why this carbocation is secondary is because the carbon that bears the positive charge is attached to two other carbon atoms. Now notice that the secondary carbocation is adjacent to a tertiary carbon. And we know tertiary carbocations are more stable than secondary ones. So there's going to be a rearrangement, a hydride shift. That plus charge wants to be on the tertiary carbon and not on the secondary one. So this hydride is going to glide towards the plus charge. And basically, they're going to trade places. And so now, the plus charge is on the tertiary carbon, and the hydrogen is now on the secondary one. But we don't need to show the hydrogen. At this point, methanol, which has a partial negative charge on the oxygen, is attracted to the carbocation. And so it's going to attack the carbon with the plus charge.
So this will be SN2? I don't know.
So we have an intermediate that looks like this. Since we have a neutral nucleophile, the reaction will at least take 3 steps to occur. But because of the carbocation rearrangement, there's 4 steps in this reaction. Now, once we form this intermediate, we're going to use another methanol molecule to get rid of the hydrogen. And so now we have the final product, which is an ether. Notice that this carbon atom is not chiral. We have 2 methyl groups. In order for a carbon atom to be chiral, it has to have 4 different groups. So this is the product. You do not need to indicate stereochemistry for this product. In fact, you can't, because this carbon atom is not chiral. So the product is an ether.
What?
Now let's try another example. By the way, if you want to find more examples on SN1 and SN2 reactions, there's a lot of other videos I've created. Check out my channel. There's one where it's basically a practice test of 75 multiple choice questions. I created it a while ago, but if you type it in, like do a search on YouTube, you should find it, and you can get a lot of practice on these types of problems. So hopefully if you watch that video, it might be very useful to you. So let's say if we have an intermediate that looks like
Just
that.
a minute.
And we're going to use water in this case.
Auf Vinted wird alles wieder neu. Hochladen und schnell wieder verkaufen.
Secondary alkyl halide with a protic solvent, and this is going to favor an SN1 reaction. By the way, protic solvents favor SN1 reactions. Polar aprotic solvents favor SN2 reactions. But let's propose a mechanism for this reaction. So we know that the bromine atom is going to leave. This is going to produce a secondary carbocation. Now, this secondary carbocation is adjacent to a quaternary carbon, which contains no hydrogen atoms. So there's going to be a carbocation rearrangement, but it's not going to be a hydride shift. Instead, it's going to be a methyl shift. The methyl is going to trade places with the positive charge. And this time, we need to show the methyl. It's not a hydrogen atom that we can ignore. So now the plus charge is now on a tertiary carbocation, or a tertiary carbon, I should say. So now we can use water to react with the carbocation. Let's not worry about stereochemistry in this example. So we're going to have this intermediate, and then the last step is to take off the hydrogen. So this is going to give us an alcohol that looks like this. So this is the product. Now, if we decide to take stereochemistry into account, do we get one product or two products? Do we need to show the stereoisomers? So look at your final product. Determine if the carbon that has the OH, if it's chiral or achiral. So we have a methyl group. Here we have a secondary carbon and a tertiary carbon. So this carbon, the chiral carbon, has 1, 2, and the left side is different from the right side because these two carbon atoms are different. So it has 4 different groups. So the carbon atom is chiral, which means that the product consists of 2 stereoisomers. The OH can be in the front, or it can be in the back. In this video, we're going to focus on the SN1 reaction mechanism. So let's say we have tert-butyl-bromide, and we wish to react it with
Wait a minute.
Iodide. What's going to be the major product in this reaction? In order to draw the major product, all we need to do is replace the leaving group with the nucleophile. In this case, the nucleophile is the iodide ion. Now let's go over the mechanism for this process. You need to know that tertiary alkyl halides favor the SN1 reaction mechanism over the SN2 reaction mechanism. So the first step is that the leaving group leaves. The substrate is ionized. And because bromine is more electronegative than carbon, when that bond breaks, bromine is going to take the 2 electrons in its bond with it. And so we're going to get a tertiary carbocation and the bromide leaving group. Now at this point, the iodide ion will react with the tertiary carbocation, giving us this product. And so that's the basic idea behind the SM1 reaction mechanism. It forms carbocation intermediates, which means that rearrangements can occur. In an SN2 reaction, there are no carbocation rearrangements. For the SN1 reaction mechanism, it's a first-order nucleophilic substitution reaction. The rate depends on the rate constant K and the concentration of the substrate, but it does not depend on the concentration of the nucleophile. So if you double the concentration of the substrate, the rate of the reaction will double. If you triple the concentration of the substrate, the rate will triple. So it's a unimolecular reaction, whereas an SN2 reaction is a second-order nucleophilic substitution reaction or a bimolecular substitution reaction. Uni means 1, bi is associated with 2. Now let's go over another example. Draw the major product for this reaction and show the mechanism as well. So let's react this alkyl halide with water. Water in this example can behave as the solvent and as a nucleophile. When the solvent behaves as the nucleophile, it's called solvolysis or solvolysis. In the first step in this reaction, the leaving group leaves. And so we're going to get a tertiary carbocation.
Yeah.
And then in the next step, water is going to attack the tertiary carbocation. Now, it can attack from the top or it can attack from the bottom. Because it has 2 different ways in which it can approach the carbocation, we're going to get 2 different types of products. So we're going to get a racemic mixture of products. So we can get the water on the front, that is like on the wedge, going out of the page, or on the dash, which means it's going into the page. Now, these 2 products are not equal. This one is the retention product, because as you can see, it's on the wedge as the alkyl halide. The other one is called the inverted product. So inversion occurred for this one. To get the inverted product, it has to attack from the back. To get the retention product, that means it attacked from the front. And now let's talk about this.
What's with all the
Die Nummer
fucking...
1 Repair-Pflegespül. Jetzt ohne zu beschweren. Gesundes Haar hat sich noch nie so leicht angefühlt.
So the bromide ion left, and so it's somewhere still
What?
close by.
How did it happen so fast? It's a 14-minute video.
To the carbocation. Now when water comes in, it can attack from the back, which will give us the inverted product, or it can attack from the front, which will give us the retention product. Now, there's nothing really stopping it from attacking in the back. Now, there is something that prevents it or slows it down from coming in the front. Because when water comes in, the oxygen atom will be the one that's being pulled towards the carbocation. The oxygen atom has a partial negative charge, and so it's attracted to the partially positive, to the carbocation, or the carbon with the positive charge. Now, as water approaches, it's going to be repelled by the bromide ion, because the bromide ion has a negative charge, and oxygen has a partial negative charge, and so those two will repel each other. So due to that repulsion of the bromide ion and the water, we are going to get less of the retention product and more of the inverted product. It could be a 60-40 ratio, and in some cases, a 70-30 ratio. You still get a mixture of these two stereoisomers. However, you do get more of the inverted product than the retention product. Now, let's finish the mechanism for this reaction. So once water comes in and attacks the carbocation,
No.
we are going to get
Why did I bite my
an oxonium ion, to the carbocation, or the carbon with the positive charge. Now, as water approaches, it's going to be repelled by the bromide ion, because the bromide ion has a negative charge, and oxygen has a partial negative charge, and so those two will repel each other. So due to that repulsion of the bromide ion and the water, we are going to get less of the retention product and more of the inverted product. It could be a 60-40 ratio, and in some cases, a 70-30 ratio. You still get a mixture of these two stereoisomers. However, you do get more of the inverted product than the retention product. Now, let's finish the mechanism for this reaction. So once water comes in and attacks the carbocation, we are going to get an oxonium ion. So basically an oxygen with 3 bonds and a positive charge. Now the last step is deprotonation. So we need to use another water molecule to take off the hydrogen atom. And so we get a tertiary alcohol. But keep in mind, we get 2 stereoisomers. So the OH group can be on the wedge, and it's going to be on the dash. So these are the 2 SN1 products that we get for this reaction. Now let's sketch an energy diagram for the SN1 reaction that we just went over. Now that particular SN1 reaction had 3 steps. So therefore there's going to be 3 transition states. The first SN1 reaction, where we had tert-butylbromide reacting with potassium iodide, it occurred in 2 steps. So for that example, we would have 2 transition states as opposed to 3. So just to draw a rough sketch for the first one, it would look something like this. This would be TS1, and this would be TS2. So for a 2-step process, you should expect to have 2 transition states. But let's focus on the last reaction that we did. So here we have the reactant, or the substrate, the alkyl halide. And then here's the second intermediate, which is the carbocation. And then after that, we had the protonated alcohol, or the oxonium species, where the oxygen had a positive charge. And our final product is the alcohol. So for a 3-step reaction, you should have 3 transition states. Keep that in mind. Now, let's move on to our next example. So here we have 2-iodo 3-methylbutane. What is the major product for this reaction? Draw the major SN1 product. By the way, the SN1 reaction occurs with the E1 reaction, but I'm not going to focus on the E1 product in this video, just the SN1 product. Now notice that we have a secondary alkyl halide, and it's adjacent to a tertiary carbon. Whenever you see that, a hydride shift will occur. So you're going to have a carbocation rearrangement. So in the first step, the leaving group is going to leave. And this gives us a secondary carbocation. And then here we have the hydrogen. And so the hydride is going to move towards the carbocation, giving us a more stable tertiary carbocation intermediate. And then the solvent is going to behave as a nucleophile, attacking that carbocation. And so we're going to have this product initially. So we have an oxygen with a methyl group and with a hydrogen attached to it. So this oxygen has a positive charge since it has 3 bonds on it. Now the next step is deprotonation. So we're going to use another solvent molecule to act as a base, removing a proton. And so our final answer is an ether. Now notice that this carbon is not chiral because we have 2 methyl groups. In order for a carbon atom to be chiral, it has to have 4 different groups. So therefore we only get one SN1 product. It doesn't matter if we put the OCH3 in the front or in the back. It will represent the same compound. Now let's consider another example. So here we have an alkyl halide, in this case a secondary alkyl halide, that is adjacent to a quaternary carbon. If we react it with, let's say, water, what's going to be the major product in this example? Draw the major SN1 product. So in this case, since we have a secondary alkyl halide next to a quaternary carbon, a methyl shift will occur. But in the first step, the bromine atom is going to leave. And so initially, we're going to get a secondary carbocation. And then in the next step, the methyl group is going to move towards the secondary carbocation. And so where the methyl came from, the positive charge will move to that position. And so now we have a tertiary carbocation. At this point, water is going to react with the carbocation.
I need to find the best way to learn math and science.
No.
It's brilliant.org.
Whoa.
Brilliant is thousands of...
No.
And then the last step is going to be the removal of a hydrogen. So now water is going to behave as a base, taking off this hydrogen. And so this is going to give us a tertiary alcohol. Now we need to determine if this carbon is a chiral carbon, and it is. It has a methyl group, an OH group, and this side is different than that side. The side towards the bottom has a methyl group. Towards the top, there are none. So because the carbon is chiral, we're going to get a mixture of stereoisomers. So we're going to get an unequal racemic mixture of these 2 products. And so that's it for this example. So watch out for carbocation rearrangements when dealing with the SN1 reaction mechanism. Now, here's another question for you.
Wait. I don't feel that good. Might be the. Oh. Should I drink a cup of coffee? Because I don't know why it's. Is it because it's so boring? I don't think so. I remember learning this before. Let me take a break just for 5 minutes. Are you serious at a time for 5 minutes? Oh, Oh yeah. And we are back just like that. So before
Or life.
wasting a lot of time, I know, but let me just complete this.
Hey.
Well, I am back in my mind.
The removal of a hydrogen. So now what is going to behave as a base taking off this hydrogen? And so this is going to give us a tertiary alcohol. Now we need to determine if this carbon is a chiral carbon, and it is. It has a methyl group, an OH group, and this side is different than that side.
I forgot what
The
chiral
side
carbon
towards the
was.
bottom has a methyl group. Towards the top, there are none.
Mm-hmm.
So because the carbon is chiral, we're going to get a mixture of stereoisomers. So we're going to get an unequal racemic mixture of these two products. And so that's it for this example. So watch out for carbocation rearrangements when dealing with the SN1 reaction mechanism. Now, here's another question for you. Consider these 3 alkyl halides. Which one is most reactive towards an SN1 reaction?
Third one.
Let me redraw this one. Put some space between the second alkyl halide and the last.
Tertiary for SN1, it's tertiary. For SN2, it's primary, if I understand.
So which of these alkyl halides is most reactive in an SN1 reaction? So you need to know that tertiary alkyl halides are more reactive than secondary alkyl halides, and methyl alkyl halides are the least reactive
For
in
SN1.
an SN1 reaction. In an SN2 reaction, the order is reversed. So here we have a secondary alkyl halide, and on this side, a primary alkyl halide. And for the third one, it's a tertiary alkyl halide. So tertiary alkyl halides are the most reactive in an SN1 reaction. And so that's what you need to keep in mind. So this one's going to be the best. Now, let's consider another example. Can SN1 reactions work for primary alkyl halides? What would you say? In most cases, no. But there are some exceptions. For example, here we have an allylic alkyl halide. primary allylic alkyl halides can work in an SN1 reaction. The key is the stability of the carbocation. The reason why normal
Just
primary
a minute.
alkyl
Nucleophilic substitution reaction.
halides like this one don't work well with SN1 reactions is because it's extremely difficult to form a primary carbocation. Primary carbocations are not stable, and so that's why this doesn't work in an SN1 reaction. The reason why tertiary carbocations are more stable than primary ones is because of the 3 methyl groups attached to the tertiary carbon. The methyl groups can donate electron density through the sigma bond, and so that is known as the inductive effect, and so they stabilize the carbocation intermediate. Another way in which a methyl group can stabilize a carbocation intermediate is through hyperconjugation. So on the right, here's a CH3.
Whoa. But won't you play?
And then this is the sigma bond of the CH bond. And so this is the empty p orbital of the carbocation. And in the sigma bond, there are some electrons. And so these orbitals can overlap, thus stabilizing the carbocation intermediate. So those are the 2 ways in which a methyl group can stabilize a carbocation: through hyperconjugation, that is overlapping of the atomic orbitals, or through the inductive effect, where it's actually donating electron density through the sigma bond. Now, once the bromine atom leaves, we're going to get a primary carbocation. But this primary carbocation is stabilized by resonance. And so this double bond can move here. And so the positive charge is shared between 2 carbon atoms. So the key to the SN1 reaction in determining if it's going to occur or not, it really comes down to the stability of the carbocation. If we can't form a stable carbocation, the SN1 reaction is not going to work. If we can, then it will work. So for the allylic alkyl halide, because we can form a stable primary allylic carbocation, that's why the SN1 reaction can work for this example. Now, it's important to understand that the primary allylic alkyl halide can also undergo an SN2 reaction, because this alkyl halide is not sterically hindered, so both the SN1 and the SN2 reaction can work with it. But let's focus on the SN1 product. So once the bromine atom leaves, we are going to get a primary allylic carbocation. And then water is going to attack the carbocation, giving us an intermediate that looks like this. And then the last step is deprotonation. So we're going to take off a hydrogen atom, and this will give us an allylic alcohol. So typically, whenever you react water with an alkyl halide, you're going to get an alcohol as a major product, regardless if it's an SN1 or an SN2 reaction. Now let's try another example. So here we have neopentobromide. If we react it with water, will this undergo an SN1 or an SN2 reaction? Now we do have a primary alkyl halide. This carbon is attached to only one other carbon. And so primary alkyl halides
Can I get the primary?
SN1 reactions work for primary alkyl halides.
I
Why
know,
tertiary
but
carbocations are more stable than
how do you know if the
sigma bond of the CH
primary
bond? And so this is the NDP orbital of the
hydrocarbon is
carbocation.
stable?
And atomic orbitals.
Most of the primary, secondary hydrocarbons are gonna have resonance, so they are supposed to be stable, if I understand. I don't know.
Through the inductive effect, where it's actually donating electron density through the sigma bond. Now, once the bromine atom leaves, we're going to get a primary carbocation. But this primary carbocation is stabilized by resonance. And so this double bond can move here. And so the positive charge is shared between two carbon atoms. So the key to the SN1 reaction in determining if it's going to occur or not, it really comes down to the stability of the carbocation. If we can't form a stable carbocation, the SN1 reaction is not going to work. If we can, then it will work. So for the allylic alkyl halide, because we can form a stable primary allylic carbocation, that's why the SN1 reaction can work for this example. Now, it's important to understand that the primary allylic alkyl halide can also undergo an SN2 reaction, because this alkyl halide is not sterically hindered, so both the SN1 and the SN2 reaction can work with it. But let's focus on the SN1 product. So once the bromine atom leaves, we are going to get a primary allylic carbocation. And then water is going to attack the carbocation, giving us an intermediate that looks like this. And then the last step is deprotonation. So we're going to take off a hydrogen atom, and this will give us an allylic alcohol. So typically, whenever you react water with an alkyl halide, you're going to get an alcohol as a major product, regardless if it's an SN1 or an SN2 reaction. Now let's try another example. So here we have neopentobromide. If we react it with water, will this undergo an SN1 or an SN2 reaction? Now we do have a primary alkyl halide. This carbon is attached to only one other carbon. And so primary alkyl halides do favor SN2 reactions. Now water is a weak nucleophile, and so that doesn't favor an SN2 reaction. Plus, it's a protic solvent, which favors an SN1 reaction. Now, the second factor that doesn't work well for the SN2 reaction is the fact that we have a quaternary carbon next to the primary carbon. And so, because of this bulky group, it's going to generate steric hindrance from to the nucleophile. It's going to be hard for the nucleophile to approach from the back because of all these three methyl groups. So all of that steric hindrance provided by those methyl groups will reduce the yield of the SN2 reaction. So in this case, we're going to get the SN1 reaction, but it's going to be a little different. The SN2 reaction can still occur, just not in good yields. So keep that in mind. So anytime you have a quaternary carbon next to a primary alkyl halide, the yields for the SN2 reaction will be lower because it's sterically hindered. Now, In a typical SN1 reaction, the leaving group will leave. But if we do this, we are going to get an unstable primary carbocation. And so that's not going to happen. So here is what's going to happen instead. The methyl group is going to attack the primary carbon, kicking out the leaving group. And by doing this, we can avoid the formation of an unstable carbocation intermediate. So rather than getting a primary carbocation, we can jump to a tertiary carbocation. And so that's what happens in this reaction. I feel like I'm missing the carbon.
I feel like I missed the whole thing.
Is the stability of the carbocation. The reason why normal primary alkyl halides like this one don't work well with SN1 reactions is because it's extremely difficult to form a primary carbocation. Primary carbocations are not stable, and so that's why this doesn't work in an SN1 reaction. The reason why tertiary carbocations are more stable than primary ones is because of the three methyl groups attached to
Steric
the tertiary
hindrance,
carbon.
if I'm right.
The methyl groups can donate electron density through the sigma bond. And so that is known as the inductive effect. And so they stabilize the carbocation intermediate.
Profile.
Another way in which a methyl group can stabilize a carbocation intermediate is through hyperconjugation. So on the right, here's the CH3.
Okay.
And then this is the sigma bond of the CH bond. And so this is the empty p orbital of the carbocation. And in the sigma bond, there are some electrons. And so these orbitals can overlap, thus stabilizing the carbocation intermediate. So those are the two ways in which a methyl group can stabilize a carbocation.
Tertiary carbon has more stable
Hyperconjugation, that is
carbon cation
overlapping
intermediate
of the
K.
atomic orbitals,
Okay.
or through the inductive
get it.
effect, where it's actually donating electron density through the sigma bond. Now, once the bromine atom leaves, we're going to get a primary carbocation. But this primary carbocation is stabilized by resonance. And so this double bond can move here.
I mean,
And so the
almost
positive charge
every...
is shared between two carbon atoms. So the key to...
I'm still... I forgot the common names. They don't have a name? Okay. I thought they have a
one
name.
reaction in determining if it's going to occur or not. It really comes down to
Alkane.
the
I
stability
think
of the
that's what I was
carbocation.
confusing.
If we can't form a stable carbocation, the SN1 reaction is not going to work. If we can, then it will work. So for the allylic alkyl halide, because we can form a stable primary allylic carbocation, that's why the SN1 reaction can work for this example. Now, it's important to understand that the primary allylic alkyl halide can also undergo an SN2 reaction, because this alkyl halide is not sterically hindered, so both the SN1 and the SN2 reaction can work with it. But let's focus on the SN1 product. So once the bromine atom leaves, we are going to get a primary allylic carbocation. And then water is going to attack the carbocation, giving us an intermediate that looks like this.
Man, the hydrogen is gonna leave.
And then the last step is deprotonation. So we're going to take off a hydrogen atom, and this will give us an allylic alcohol. So typically, whenever you react water with an alkyl halide, you're going to get an alcohol as a major product, regardless if it's an SN1 or an SN2 reaction. Now let's try another example. So here we have neopentobromide. If we react it with water, will this undergo an SN1 or an SN2 reaction? Now we do have a primary alkyl halide. This carbon is attached to only one other carbon. And so primary alkyl halides do favor SN2 reactions. Now water is a weak nucleophile, and so that doesn't favor an SN2 reaction. Plus it's a protic solvent, which favors an SN1 reaction. Now the second factor that doesn't work well for the SN2 reaction is the fact that we have a quaternary carbon next to the primary carbon. And so because of this bulky group, it's going to generate steric hindrance from to the nucleophile. It's going to be hard for the nucleophile to approach from the back because of all these three methyl groups. So all of that steric hindrance provided by those methyl groups will reduce the yield of the SN2 reaction. So in this case, we're going to get the SN1 reaction, but it's going to be a little different. The SN2 reaction can still occur, just not in good yields. So keep that in mind. So anytime you have a quaternary carbon next to a primary alkyl halide, the yields for the SN2 reaction will be lower because it's sterically hindered. Now, in a typical SN1 reaction, the leaving group will leave. But if we do this, we are going to get an unstable primary carbocation. And so that's not going to happen.
So one of the metal is gonna join here.
So here is what's going to happen instead. The methyl group is going to attack the primary carbon, kicking out the leaving group. And by doing this, we can avoid the formation of an unstable carbocation intermediate. So rather than getting a primary carbocation, we can jump to a tertiary carbocation. And so that's what happens in this reaction.
And it favors SN2.
I feel like I'm missing a carbon. Let's see. 1, 2, 3, 4, 5.
Yeah.
I want to make sure I had that right. So now the water is going to attack the carbocation, giving us this intermediate. And we know the final step is the removal of a proton. So therefore, our answer, we can draw it like this. So we only get one major SN1 product. And we don't have a chiral center, so we're not going to be concerned with stereochemistry. Now, here's another question for you. Consider these three substrates. Which one works the best for an SN1 reaction? Feel free to pause the video.
The last one.
So notice that all of these alkyl halides are secondary alkyl halides.
But that one
And on
does
the right,
not have.
They're all next to a primary alkyl halide.
But on the left.
But on the left, it's different. Here we have a secondary carbon.
Yeah.
Here is a quaternary carbon.
Tertiary.
And this is a tertiary carbon.
Yeah.
So right now, this is going to be the worst for an SN1 reaction. Even though they're all secondary alkyl halides, this cannot undergo a rearrangement.
I thought it was.
Now, these two, they're very good for an SN1 reaction.
I think I confused.
This one can undergo a hydride shift, and this one can undergo a methyl shift. And so they both can generate a tertiary carbocation. So in that sense, they're similar. However, the SN1 reaction usually competes with the SN2 reaction. And this is terrible for an SN2 reaction because there's a lot of steric hindrance due to the quaternary carbon. So because the SN2 reaction is less competitive, this is going to be a better option we should get a better yield for the SN1 reaction, even though both of them can lead to the same tertiary carbocation intermediate.
But
So here is another question for you.
Okay,
I want you to determine which of these alkyl halides work the best for an SN1 reaction.
Fucking hell. How many ads, bro? How many fucking ads? Someone full reaction. 77 test questions. If I remember, I had to sign in, right?
So in the
These two are same.
example, we have an aryl halide, and here we have a vinyl halide. And then for this one, we have a benzoyl halide, and this is another benzoyl halide. So which one is the best for an
Iodide.
SN1 reaction?
I must say this one's the best.
So this carbon is secondary. This carbon is primary. This one is secondary. And this is secondary. So you might be thinking we could eliminate the primary carbon. And you won't be wrong for doing that. Now, you need to know that aryl halides and vinyl halides, they do not work for SN1 reactions or SN2 reactions. So we can eliminate those options.
Okay. So I was wrong.
Now, these two, they have the same structure. Benzoyl halides work very well for SN1 and SN2 reactions. So the real thing we need to look at is the leaving group. Which leaving group is better, the bromide ion or the iodide ion? If we look at the halogens, fluorine, chlorine, bromine, and iodine, we know that in a periodic table, as you go down, atomic size increases. So iodide is bigger than bromide.
Yep.
And iodide is the better leaving group because of that.
So
because iodide is bigger than the bromide ion, it can stabilize the negative charge better. If you can spread out a negative charge over a larger area, that process will be more stable than concentrating a negative charge in a smaller area. And so larger ions can stabilize a negative charge better than smaller ions can. And so for this reason, iodide is a better but a better leaving group than bromide. And bromide is a better leaving group than chloride. And fluoride is not a good leaving group. So leaving group stability corresponds with
atomic size.
So in this case, this is the best alkyl halide for the SN1 reaction compared to all the other options that we have here.
Mm-hmm.
Wie knusprig.
God damn it, damn it, damn it, damn it, damn it. God damn it.
have a nucleophile reacting with the substrate. The nucleophile is hydroxide. It has a negative charge, and the substrate is the alkyl halide. Bromine is more electronegative than carbon, so bromine bears a partial negative charge, carbon bears a partial positive charge. So the nucleophile is attracted to the partially positive carbon atom, and so it approaches it from the back, and as it attacks the methyl group, the bromine group gets expelled. And so we get the product, which is methanol, and we also get a side product, also known as the leaving group, which is the bromide ion. And so that's the basic idea behind the SN2 reaction mechanism.
There's no
To draw the
intermediate.
transition state, it looks like this. So here we have the 3 hydrogen atoms attached to the carbon, and we have a bond being created between the oxygen and the carbon atom, and a bond that's breaking between the carbon and the bromine atom. And so the transition state looks like this. Carbon bears a partial positive charge, bromine bears a partial negative charge, and the same is true for hydroxide. Now let's go over some other reactions that is associated with the SN2 mechanism. What do you think the major product for this reaction will be? Let's say if we have butyl bromide and we wish to react it with sodium methoxide. Now what you need to realize is that the sodium ion is a spectator ion, so it's not going to do anything in the reaction. The nucleophile is the methoxide ion, and so what it does is it attacks the carbon from the back, that is away from the bromine atom, and then it expels the bromine atom. Now it doesn't want to attack from the front because bromine has a partial negative charge,
And it
and
repels.
the oxygen atom has a negative charge. So if it tries to approach from the front, it's going to be repelled by the electronegative bromine atom. So instead, it attacks from the back. Therefore, we're going to get this product, which is an ether. Now let's work on some other examples. Let's say we have, in this case, 2-bromobutane, and let's react it with potassium iodide in acetone. Acetone is a polar aprotic solvent. There are no OH or NH bonds. And it turns out that polar aprotic solvents, they enhance SN2 reactions. What do you think the major product for this reaction will be? So first, we need to identify the nucleophile. The nucleophile is the iodide ion. And so what it's going to do is it's going to approach the carbon from the back, expelling the leaving group. Now notice that we have a chiral center. And notice that the bromine is on the wedge. So now, because the iodide ion approached from the back, it's going to be basically on the dash. So this means the bromine atom is coming out of the page, and the iodide ion,
It's into the
or
page.
the iodine atom, is going into the page. And so this is the product of the reaction. For an SN2 reaction, we get inversion of configuration. So as you can see, the stereochemistry changes. This was R2-bromobutane, and now we have S2-iodobutane. Now here's another example. So let's say we have the chair conformation of 1-bromo, 3-methyl cyclohexane. Let's say the methyl group is in the equatorial position and the bromine atom is in the axial position. Draw the major SN2 product for this reaction. Let's use sodium cyanide in DMSO, dimethyl sulfoxide, which is another type of polar aprotic solvent that enhances an SN2 reaction. So go ahead and predict the major product for that reaction. So we know the cyanide ion, which looks like this. It's basically a triple bond between the carbon and the nitrogen atom, but the carbon atom bears the negative charge, so it's the nucleophilic center. It's going to attack the carbon from the back, expelling the leaving group.
Oh, I heard a new method to skip the ads. Yes, it did work. Stop. 30 minutes. You know what? I need to take that 5 minute break. I don't know if it's so boring or is it me? I think I have a problem. I'm not being able to focus. Let me take that 5 minute break. Hey Siri, set a timer for 5 minutes. Oh shit. Stop, stop.
And notice that the bromine is on the wedge. So now, because the iodide ion approached from the back, it's going to be basically on the dash. So this means the bromine atom is coming out of the page, and the iodide ion,
Yeah, the
or
text from
the
the
iodine
back.
atom,
I
is going into the
understand.
page. This was R2-bromobutane, and now we have S2-iodobutane. Now here's another example. So let's say we have the chair conformation of 1-bromo, 3-methyl cyclohexane. Let's say the methyl group is in the equatorial position and the bromine atom is in the axial position. Draw the major SN2 product for this reaction. Let's use sodium cyanide in DMSO, dimethyl sulfoxide, which is another type of polar aprotic solvent that enhances an SN2 reaction. So go ahead and predict the major product for that reaction. So we know the cyanide ion, which looks like this. It's basically a triple bond between the carbon and the nitrogen atom. But the carbon atom bears the negative charge, so it's the nucleophilic center. It's going to attack the carbon from the back, expelling the leaving group.
Auf Vinted wird alles wieder
No.
neu. Einfach.
Did not work.
Ich sag Racket.
The cyanide group is going to be on the equatorial bond because the bromine atom was on the axial bond, and so you need to switch it. And so the product, let me put over here where I have more space. The product will look like this. So the methyl group is unaffected, and now cyanide is in the equatorial position. And so this is the SN2 product for this reaction. The SN2 reaction is a second order nucleophilic substitution reaction. The rate of the reaction depends on the concentration of the substrate and the concentration of the nucleophile. So if we double the concentration of the substrate, the rate will double. If we triple the concentration of the substrate, the
No.
rate will
I
triple.
think I've seen this video
If we double
just
the
10 minutes
concentration of the
before,
substrate and double the
but I
concentration
need
of
to
the
see it
nucleophile,
again because I did not
2
understand.
times 2 is 4, so the rate will increase by a factor of 4. If we triple the concentration of the substrate, quadruple the concentration of the nucleophile,
Makes it 12
the rate
times.
will increase by a factor of 12. So it's first order in the substrate, first order in the nucleophile. Overall, the rate is second order if you add 1 and 1, which gives you 2. Now the energy diagram for the SN2 reaction looks like this. There's only one transition state, so here it is. This is the energy of the reactants, this is the energy of the products, and on the y-axis we have the energy. On the x-axis we have the progress of the reaction. The activation energy is the difference between the energy of the reactants and the transition state. Now, it's important to understand that The SN2 reaction is a concerted reaction mechanism. Everything happens in one step. All the bond making and bond breaking processes occur together, and so it's a concerted reaction mechanism. Now here's a question for you. Consider the following alkyl halides. Which of these alkyl halides is most reactive in an SN2 reaction, and which one is the least reactive? Feel free to pause the video and answer that question. So here we have a secondary alkyl halide because the carbon that bears the bromine atom is attached to two other carbon atoms. And in the middle, we have a tertiary alkyl halide because that carbon, which is here, is attached to three other carbon atoms. And on the right, we have a primary alkyl halide because the carbon that bears the bromine atom is attached to one other carbon atom. It turns out that the primary alkyl halide is the best for an SN2 reaction,
Yup.
whereas the tertiary alkyl halide is the worst. And the reactivity is
Where's
as
the
follows.
E1, E2?
A methyl alkyl halide is better than a primary alkyl halide, which is better than a secondary alkyl halide, which is better than a tertiary alkyl halide. Now let's talk about why.
I've been all around town, being stunning.
On the four main types of reactions that you'll see in a typical organic chemistry course. So let's say if we have an alkyne. If we convert it into an alkene, if you go from, let's say, a triple bond to a double bond, or from a double to a single bond, going in this direction, it's an addition reaction. And going from, let's say, an alkane to an alkene, it's an elimination reaction.
Okay.
Now, let's see why that's the case. So let's say if we have cyclohexene. In order to convert this into cyclohexane, we need to add two hydrogen atoms. So here we're going to add hydrogen gas using a metal catalyst. We're going to add two hydrogens across the double bond. And so this is an addition reaction because we're adding something to the molecule. We're adding two hydrogens to it. Now let's say we have this molecule, 2-butanol, and we're going to react it with concentrated sulfuric acid with heat. So this is going to favor an elimination reaction. And so what's going to happen is we're going to remove or eliminate a hydrogen atom and the hydroxyl group, giving us an alkene. And so we're going from a single bond to a double bond. And whenever you see that, it's an elimination reaction. In order to go from a single to a double bond, we need to eliminate or remove two substituents. And when you remove hydrogen and an OH group, you're basically removing water. So this is also called a dehydration reaction.
What? Say what?
Hexane. We need to add two hydrogen atoms. So here we're going to add hydrogen gas using a metal catalyst. We're going to add two hydrogens across the double bond. And so this is an addition reaction because we're adding something to the molecule. We're adding two hydrogens to it. Now let's say we have this molecule, 2-butanol, and we're going to react it with concentrated sulfuric acid with heat. So this is going to favor an elimination reaction. And so what's going to happen is we're going to remove or eliminate a hydrogen atom and the hydroxyl group, giving us an alkene. And so we're going from a single bond to a double bond. And whenever you see that, it's an elimination reaction.
We eliminate
In
the
order to go from a
hydrogen
single to a
and
double bond, we need to eliminate or remove two substituents.
to
And when you
eliminate
remove
we need
hydrogen
energy.
and an OH group, you're basically removing water.
Makes sense.
So this is also called a dehydration reaction.
Makes sense.
Now let's say if we have this molecule, 2-chloropentane, and let's react it with water. One of the products that we can get in this reaction will be 2-pentanol. And what type of reaction do you think this is? Notice that we replace a chlorine atom with an OH group. So we've substituted the chlorine atom with an OH group. So this is called a substitution reaction. Now, there's one other type of reaction that you need to be aware of. So let's say we have a secondary carbocation. The reason why it's secondary is because the carbon that bears the positive charge, that carbon is attached to two other carbon atoms. Now, notice that the secondary carbocation is adjacent to a more substituted tertiary carbon. Whenever you see that, a rearrangement will occur. And the reason why the rearrangement occurs is to form a more stable carbocation intermediate. Tertiary carbocations are more stable than secondary ones. And so this is a carbocation rearrangement. So those are the four main types of reactions that you need to be familiar with. Addition reactions, where you go from, let's say, a double bond to a single bond by adding something, by adding two groups across a double bond. There's the elimination reaction, which is the reverse of an addition reaction, going from a single to a double by removing two groups. And then you have substitution, where you replace a group with another group, and then a rearrangement, where the whole molecule just rearranges. Like nothing is added or subtracted, it's just things move around in the molecule or ion. Now let's go over some practice problems. And I want you to determine the type of reaction that we're dealing with. So on the left, we have 1-butene, and we're going to react it with hydrobromic acid. What do you think the product of this reaction will be? Feel free to pause the video, write the product of the reaction, and also write up a mechanism for it and determine what type of reaction we're dealing with.
Wait, it's SN2?
This reaction, the hydrogen atom will go on the less substituted
I
carbon
don't think
atom,
that was the question. I think it's addition.
primary carbon, and the bromine atom will go on a more substituted carbon atom of the double bond. So we're going from a double bond to a single bond.
Yeah.
So we know that this
Addition.
is an addition reaction. As you can see, we are adding a bromine atom and a hydrogen atom. Now, HBr is an electrophile. Acids tend to be electrophiles, bases, they tend to be nucleophiles. And so this is specifically called an electrophilic addition reaction because we're adding an electrophile to an alkene. Now let's talk about the mechanism for this reaction. So the first thing that's going to happen is the nucleophile, which is the alkene, is going to acquire the hydrogen atom, expelling the bromide ion. And so this will give us a secondary carbocation intermediate because we've added the hydrogen to the primary carbon. And then in the last step, the bromide ion will combine with the carbocation. And so the product for this reaction will be 2-bromobutane. And we don't need to show the hydrogen. So that's the mechanism for this reaction. Now let's say if we have cyclopentanone and we decide to react it with sodium borohydride followed by H2O. What's going to be the product of this reaction? Sodium borohydride is a reducing agent. By the way, feel free to pause the video as I go through these examples if you want to try it.
Elimination.
Now, we're going to get an alcohol in this reaction. So what type of reaction is this if we're going from a ketone
So that was addition.
to an alcohol? So notice that we had a double bond, and now it's a single bond. So just by seeing that, you know that this
Could be.
is an addition reaction.
Okay.
But what type of addition reaction are we dealing with?
No idea.
Well, we know it's an addition, first of all, because we've added a hydrogen to the oxygen, and we also added this invisible hydrogen to the carbon, because carbon needs to have 4 bonds. So we've added H2 across the carbonyl group. So that's why it's an addition reaction. Now, sodium borohydride has a sodium ion and a boron atom surrounded by 4 hydride ions. Now, the boron atom has a negative formal charge, but if we consider the boron hydrogen bond, boron has an electronegativity value of 2.0, and hydrogen has a value of 2.1. So hydrogen is slightly more electronegative than boron, so it carries a partial negative charge, and boron carries a partial positive charge. Partial charges and formal charges are not the same thing. A partial charge is based on the electronegativity differences between an element and what that element is bonded to, whereas a formal charge is something that we assign to an element based on the number of bonds and lone pairs that it has. So they're not the same thing. Now, BH4 minus, the borohydride ion, it's basically a boron attached to a hydride ion. And because this hydrogen has a negative partial charge, it's nucleophilic. And so we've added a nucleophile to this carbonyl group. So this is not just called an addition reaction, but it's also called, more specifically, a nucleophilic addition reaction, because we're adding a nucleophile to the carbonyl group. So now let's write up a mechanism for this reaction. So in the first step, the borohydride ion will release a hydride ion to attack the carbonyl group. And so we're going to add the first hydride ion to the carbonyl carbon. So here it is. Now, we're going to have a single bond between the carbon and the oxygen. And so this oxygen now has a negative charge, at which point we can react it with water. So it's going to pick up a hydrogen from water, generating the hydroxide ion. And so now we've added a total of 2 hydrogen atoms across the carbonyl group, making it an addition reaction. And so that's the mechanism for the reduction of a ketone into an alcohol using sodium borohydride, which is a nucleophilic addition reaction. Now, for those of you who might be studying for the organic chemistry final exam, I have a video that can help you, and it's on my Patreon page. If you go to patreon.com/mathsciencetutor, you can access that page. And if you scroll down, there's a lot of other videos I have here too, but let's say if you're taking the first semester of organic chemistry, I have a 6-hour video that can help you with that if you decide to become a patron. Now, on YouTube, I have a free 2-hour trailer version of this video, but if you want the entire 6-hour video, you can access it here or on Vimeo as well.
Imagine being able to build anything just by thinking about it.
I'm not
The
imagining.
base for
I'm not imagining.
The second semester of organic chemistry, I have an 8-hour video that you can access as well. And there's some other stuff here that you could find too. If you're taking Gen Chem or physics, I have stuff on that as well. So that's it, just in case you're interested. Now, what about this example? What's going to happen in this reaction? So notice that we have a secondary carbocation next to a tertiary carbon. And so we know what the end result is. A carbocation rearrangement. But how does it happen? A hydride will move from the tertiary carbon to the secondary carbon. And so it's going to move here. And by doing so, the positive charge is going to move towards where the hydride left. And so we have a carbocation rearrangement. So whenever you have a tertiary carbon adjacent to a secondary carbocation, a hydride shift will occur. Now here's another example of a rearrangement reaction. So this time, we have a secondary carbocation next to a quaternary carbon. So instead of a hydride shift, we're going to get a methyl shift. So the carbon structure, the carbon backbone of this ion will change. So now we have a tertiary carbocation. So that's when a methyl shift will occur. You have to have a quaternary carbon next to a carbocation. Another type of rearrangement is the ring expansion. In this example, we have a 5-carbon ring, and so it's going to expand to a 6-carbon ring, which is more stable. And so we can break either this bond or this bond, it really doesn't matter. Let's call this carbon 1, 2, 3, 4, 5, 6. So this is going to expand to a 6-carbon ring. Now, where's the plus charge? Well, first, let's put the methyl group somewhere. So this methyl group here is attached to carbon 1. So this has to be 1. Let's call this 2, 3, and so forth. Now, notice that we broke the bond between carbons 2 and 6. And then we're going to reform a bond between carbons 1 and 6. So carbon 2 lost the bond, but it didn't regenerate a new bond. So carbon 2 has the positive charge. So right now, we have a secondary carbocation next to a tertiary carbon. So what do you think is going to happen? Well, we know what's going to happen, a hydride shift. And so now, not only do we have a more stable 6-membered ring, but we also have a tertiary carbon.
How did it go
a tertiary carbocation
from
instead of a secondary
5
carbocation.
to 6 ring?
And so, trail of that. So that's when a methyl shift will occur. You have to have a quaternary carbon next to a carbocation. Another type of rearrangement is the ring expansion. In this example, we have a 5-carbon ring. And so it's going to expand to a 6-carbon ring, which is more stable. And so we can break either this bond or this bond, it really doesn't matter. Let's call this carbon 1, 2, 3, 4, 5, 6. So this is going to expand to a 6-carbon ring.
Ah.
Now, where's the plus charge? Well, first, let's put the methyl group somewhere. So this methyl group here is attached to carbon 1. So this has to be 1. Let's call this 2, 3, and so forth. Now, notice that we broke the bond between carbons 2 and 6.
Yep.
And then we're going to reform a bond between carbons 1 and 6. So carbon 2 lost the bond, but it didn't regenerate a new bond. So carbon 2 has the positive charge. So right now, we have a secondary carbocation next to a tertiary carbon. So what do you think is going to happen? Well, we know what's going to happen, a hydride shift.
Oh.
And so now, not only do we have a more stable 6-membered ring, but we also have a tertiary carbon a tertiary carbocation instead of a secondary carbocation. Mm-hmm. And so the driving force for a rearrangement reaction is stability. So if you have a 5-carbon ring, it's going to expand to a 6-carbon ring if it can, because it can reduce its potential energy, becoming more stable. And if you have a secondary carbocation, it's going to rearrange to a tertiary carbocation if it can, because tertiary carbocations are more stable. They are lower in energy. And so the driving force for any rearrangement reaction is usually stability. A molecule will try to rearrange itself in order to find its lowest energy state. Now, let's say if we have a secondary alkyl halide and we decide to react it with water. And we're going to use heat as well. Now, we can get a mixture of products here, but I'm going to focus on one of the 2 main products that we can get. One of the products that we can get is an alkene. The other product we can get is an alcohol. So what type of reactions do we have here? If we get the alcohol, it's a substitution reaction because we've replaced the bromine atom with an OH group. But now let's focus on this product. What type of reaction do we have here? In order to form a double bond, we had to remove or eliminate the hydrogen and the bromine atom. So this is an elimination reaction. Specifically, it's called the E1 reaction, a first order elimination reaction, because the rate of the reaction depends only on the concentration of the substrate and not the concentration of the base.
Want to meet me and win tickets to the Lifetime Tour? Max.
God damn it.
So for the E1 reaction, the first step is that the leaving group leaves. And so we're going to get a carbocation intermediate. And then in the next step, the base, which is water, is going to abstract a proton, forming a double bond. And so that's how we can get the alkane. So remember, anytime you go from a single bond to a double bond, it's going to be an elimination reaction. Now let's use the same alkyl halide, but this time, instead of using a weak base like water, let's use a strong base like hydroxide, but dissolved in water. So what's going to be the major product in this example? The strong base will immediately go for the hydrogen, forming a double bond, kicking out the leaving group, all in one step. So this is a concerted reaction mechanism. No carbocation intermediates will form, and so we can't have any carbocation
I
rearrangements.
believe SN1 has
And this is going to go straight to the alkene.
intermediate.
Now, in addition to getting transbutene, we can also get cisbutene. We could also form the double bond here. However, this is going to be the major product, also known as the Zaitsev product. This product is the minor product, which is called the Hoffman product. But overall, this is an elimination reaction because we're going from a single to a double bond, and we've eliminated the hydrogen and the bromine atom. So we've removed HBr from the equation. So this is called the E2 elimination reaction. It's a second order it's a second order elimination reaction. The rate depends on the concentration of the substrate, that is the alkyl halide, and the concentration of the base, which in this case is hydroxide. So it's first order with respect to the substrate, first order with respect to the base. 1 plus 1 is 2, so it's second order overall. So it's a second order elimination reaction. Now let's say if we have a molecule that looks like this. So this is called a beta hydroxy ketone. With respect to ketone, this is the alpha carbon and this is the beta carbon. So on the beta carbon, we have a hydroxyl group. So that's a beta hydroxy ketone. And we're going to react it with a base, hydroxide, and we're going to heat it. Now, the alpha hydrogen is relatively acidic. And the reason for that is because the conjugate base is stabilized by resonance. So in this reaction, the base is going to remove the acidic alpha hydrogen, giving us an enolate ion. So right now we have a carbon with a negative charge on it, but that negative charge is stabilized by resonance. We can take this lone pair, form a pi bond, and push a negative charge on the oxygen. And so this is called an enolate ion. Now, in the next step, the oxygen can use one of its lone pairs to reform a pi bond, causing this double bond to move here, expelling the OH group. And so in this reaction, we're kicking out a poor leaving group, and we're also getting rid of a hydrogen atom. So what type of reaction is this? So this is our final product. Notice that we formed a double bond between the alpha and the beta carbon by eliminating or removing H and OH. So this is an elimination reaction. Specifically, it's called the E1CB reaction, when you have to remove a poor leaving group. So our product is an alpha-beta unsaturated ketone. And so that is the E1CB reaction, another elimination reaction. Now let's move on to our next example. So let's say that we have 1-bromobutane, and let's react it with hydroxide. So what's going to happen in this reaction? So we have a primary alkyl halide. And so this is going to favor the...
Again, my mind is flushed with a lot of stuff. Be right back. A 10-minute break. Be right back. Yo, what's up, people? I accidentally overused my time. Please, we're back. How many hours did I waste? I think I wasted 1 hour. About 1 hour.
Into reaction over the E2 reaction. If we had a secondary alkyl halide and we use a strong base, this would favor the E2 reaction. The SN2 reaction stands for second order nucleophilic substitution reaction. So that tells us that we're going to replace or substitute the bromine atom with the OH group. And that's what's going to happen. The hydroxide ion will attack the carbon from the back, expelling the leaving group. And so we're going to get 1-butanol. So we've substituted the bromine atom.
Wait. That's the normal one. I need the better one. Okay, the first lecture itself is spectroscopy. Then which? Now reaction. Carbocation, substitution, addition, electrophilic, stereo. Okay. PDFs is there? 9 PDFs. Okay. Oh, there's an exam on 12th of December, but no, don't hope for that. Why did I see that? God damn it. Electronic structure and bonding, nomenclature, functional groups, electronic properties, acid-base properties, arrangement in space. Determining structures by spectroscopy, spectrometry, basic principles, interaction of rays or waves with molecules, X-ray diffraction, scattering of X-rays gives bond length and angles, UV UVV spectroscopy, absorption of ultraviolet and visible waves by valence electrons. When I say valence electron, it's the electron at the outermost shell. Valence electrons are the electrons at the outermost shell. Okay, that was right. IR spectroscopy, absorption of infrared waves due to vibration and rotation. NMR spectroscopy, interaction of radio waves with nuclei in a magnetic field. Interaction of the radio waves with the nuclei in magnetic field. I do remember learning what NMR spectroscopy is. It's a form of graph or fingerprint on how molecular bonds interact with infrared light. By analyzing it, you could figure out what functional group the molecule contains. The graph basically for infrared spectroscopy. Oh, that's IR. NMR spectroscopy is a technique that uses magnetic properties of certain atomic nuclei to give detailed information about the structure of the molecule, especially the arrangement of atoms and chemical environment around them. I do remember searching up how it works, but now I don't remember the definition of NMR spectroscopy. We could look it up. Mass spectroscopy, determination of mass of a molecule or its fragments. No interaction with light waves, no spectroscopy. Okay. Mass spectroscopy, how does that work? Determining structures by spectroscopy, spectrometry. Basic principles. Ultraviolet rays, cosmic rays has the highest frequency wavelength. Could you explain? This comes up a lot in spectroscopy since almost every technique, IR, UV, depends on how light interacts with matter, the distance between two consecutive peaks of a wave. That's the wavelength. Okay. Frequency is the number of wave cycles passing a point per second. So frequency in terms of peak, how would you describe it's the number of peaks. So they both no, yeah. So cosmic rays have short wavelength, high frequency. Radio waves have long wavelength, low frequency. Microwaves, visible light. Determining structures by spectroscopy. X-ray crystallography. Crystal structures can be determined by allowing samples of crystalline compounds to diffract X-rays from resulting characteristic diffraction patterns. It is possible to deduce the precise spatial arrangement of atoms in a molecule. So X-rays can be only so. X-ray diffraction crystals. Determining structures by I mean that's the explanation for that. So what kind of questions can I expect from this part for my exam? Well, I gotta eat something. Looks like I gotta eat something. And what? I shall play the game and go cook, eat. Gotta search for jobs. The biocoding stays put for a while because I need to first figure out how should I use my time according to my Twitch follower and friend Clono Pin Commander. That was a good point that it's better to inquire how should I take this further before. Okay. Yep. So YouTube stream, I'm gonna end it, but I'll be back